Welcome to another new video of interesting math problem on our channel Math Solutions for You. Please do like, share, comment, and don't forget to subscribe to our channel. ABCDEF is a regular hexagon. If area of triangle ACE is 50, what is the area of hexagon ABCDEF? We start this problem with the formula which basically describes what would be the sum of angles of an n-sided convex polygon. And the convex term basically ensures that none of the angles of the polygon is a reflex angle. So it's a convex n-sided polygon, and the sum of all the angles of the polygon is given by this formula. It's basically n minus 2 multiplied by 180 degrees. And you can check, for example, for a triangle, n will be 3. So the sum will be 3 minus 2, which is 1, multiplied by 180 degrees, which makes sense, right? Because the sum of angles of a triangle are 180 degree. So for a quadrilateral, n is 4, so that makes 4 minus 2 equal to 2 multiplied by 180 degree, which is 360 degrees. Again, it makes sense. So this is a generic formula for sum of angles of an n-sided convex polygon. For a hexagon, of course, n is 6. So the sum of the angles will be 6 minus 2 multiplied by 180 degrees, so which comes to 720 degrees. And then, since this is a regular hexagon means that all of the sides of the hexagon are equal, and so are each of the angles, each of the 6 angles. So for getting to what the value of each angle of the hexagon, of the regular hexagon will be, we just divide this number by 6, the sum by 6, and we get 120 degrees. So basically, here we have this angle ABC within the hexagon, and each of those angles will be equal to 120 degrees. So since this is a regular hexagon, we know that the sides of the hexagon are also equal. So let's consider, one of those triangles. Let's consider triangle ABC. So side AB is equal to side BC. So that makes ABC an isosceles triangle, right? Because two of its sides are equal. So angle BCA will be equal to angle BAC. And since the angle included between the two equal sides of this isosceles triangle is 120 degrees, we can very easily find what the other two angles would be, the two equal angles will be, by subtracting this angle from 180 degrees and then divided by 2. So basically we do 180 minus 120, which comes to 60, and then we divide by 2. So we get the value of each of those two equal angles of the isosceles triangle, which are marked in green, as 30 degrees. So another thing to note here is, since this is a regular hexagon, the 3 triangles that we have here in this figure, triangle ABC, triangle CDE, and triangle AFE, will be congruent. And this could be actually very easily proved through SAS congruency, because this is a regular hexagon, so each of those sides, AB, BC, will be equal to the corresponding sides of those other two triangles. For example, if we consider ABC and CDE, then AB is equal to CD, and BC is equal to DE, and the included angles ABC and angles CDE will be each equal to 120. So that makes those two triangles congruent by SAS. And Similarly, we can also show that triangle AFE is congruent to triangle CDE. So all of those three triangles are congruent. And it's pretty apparent from symmetry if you don't want to do the actual proof. So next, consider what's the implication of this. So the implication of this is basically AC is equal to CE is equal to AE, because these are corresponding sides of those congruent triangles, so they will be equal. And that makes triangle ACE an equilateral triangle because all of its sides, AC, CE, and AE, are equal. Now we'll consider the centroid of this equilateral triangle. And for an equilateral triangle, it's actually super easy because the centroid will be also the point where the altitudes of the triangle meet, because centroid is the point where the medians meet, and in case of the equilateral triangle, the median is also the altitudes. It's all very perfectly symmetrical. So let's draw that centroid and let's join, let's call the centroid as O, and let's join the vertices A, C, and E to the point O. So essentially, from symmetry, we can say that, well, there are now three equal triangles, three congruent triangles, formed by joining the vertices A, C, and E to the centroid. And these are triangles OAC, triangle OCE, and triangle OEE. So these are all equal congruent triangles that we have formed by joining the vertices to the centroid of this equilateral triangle ACE. We also know that the value of each of those angles marked in red should be essentially equal to half the angle of the equilateral triangle. For example, angle OCA will be essentially half of angle ACE, because in this case, since it's an equilateral triangle, the median will actually bisect the angle, right? So each median will bisect, the opposite angle, and so each of those angles marked in red will be half of 60 degrees because it's equilateral. So the whole angle, angle ACE, for example, is 60. So that makes angle OCA half of 60, which is 30. So each of those angles will be equal to 30. Now consider triangle ABC and triangle OAC. Now, two of the corresponding angles of those two triangles are equal and they have a common side, right? That makes triangle ABC and triangle OAC congruent by angle side congruency, AAS congruency. But we know that OAC, that's basically 1/3 of triangle ACE, because O is the centroid of the equilateral triangle, and for an equilateral triangle, it's all very nice and symmetric. So the centroid basically divides the triangle into three equal triangles, and each of those will be 1/3 of the whole triangle. So that makes triangle OAC equal to 1/3 of triangle ACE. But we have shown that triangle OAC is congruent to triangle ABC. So essentially, that makes triangle ABC, the area of the triangle ABC, being equal to 1/3 of that of triangle ACE. So now let's focus on what's the area of the hexagon. Of course, it includes the area of the equilateral triangle ACE, but it also includes the area of the three other triangles, ABC, CDE, and AFE. And we know that those three triangles are congruent and they're equal, so they should be of equal area. So we can simply write the area of the hexagon as area of triangle ACE plus 3 times area of triangle ABC. And from the previous step, we have found out that the area of triangle ABC is 1/3 that of triangle ACE. So if we substitute that, this becomes triangle ACE plus 3 times 1/3 of the area of triangle ACE. And this, when simplified, simply becomes 2 times the area of triangle ACE. And it's given in the problem that area of triangle ACE is 50. So the area of the hexagon is simply 2 multiplied by 50, which is 100. So the correct answer in this case will be option A, 100.